We're Group 5 and our product is StanSmart insoles. Group 5 consists of Kylie Kreis, Andrew Johnston, Lexi Johnson, and Paulina Pay.
StanSmart insole is a product that introduces an everyday and affordable way to keep track of personal posture. Most people are not aware of how they stand or walk, and if their posture is not correct, it can lead to many issues. Ideal foot posture consists of properly aligned feet facing forward, rather than one or both feet turning inward or outward. Bad posture can potentially cause foot and ankle problems by placing stress on different parts of the feet and causing circulation issues. The feet and ankles may swell due to poor blood flow, and the bones and ligaments will struggle to handle the shifting weight load, potentially causing pain and other issues. Foot positioning can place excessive stress on knee and hip joints, which connects to the posture habits in the lower and upper back area. Poor posture in the feet could have extensive negative effects on the whole body. Our product is an insole that provides data that can be used to solve incorrect posture problems using flexible force sensors. These sensors will be used to track weight distribution in certain areas of the foot while the user is standing. The sensors will detect the weight distribution in the ball and the heel of the foot. In addition, using the 6-axis gyro sensor, the foot progression angle, also known as FPA, the pronation, the supination, the dorsiflexion, and the plantar flexion will be determined.
The principle behind using a flexible force sensor is that when force is applied, there will be a related output voltage. The flexible force sensor is a resistive element, and when force is applied, the resistance value lowers. When implementing the FlexiForce sensor as one of our sensors in a voltage divider, there will be a related output voltage. A non-inverting operational amplifier was used to amplify the output voltage, and a microcontroller can then read the output voltage and calculate the corresponding weight. The principle behind using a 6-axis gyroscope sensor is that a gyroscope can help indicate orientation. The microcontroller gets measurements directly from the sensor. The technical analysis used to justify this method was a multi-sim simulation. A variable resistor was placed in the simulation for R4 instead of the actual flexible force sensor because the part was not available in the software. An application note on the force sensor datasheet instructed not to operate the sensor higher than a 3.3 voltage in a voltage divider circuit, so the input voltage was limited to 3 volts. Calculations were done to decide the resistor values of R3, R2, and R1 and calculated the gain, and the multi-sim simulation was run to see that the output voltage would theoretically produce a linear relationship between applied force and an output voltage.
We begin our demonstration demonstrating pronation and supination. As our test subject begins to lift her foot and turn her foot inward, our code displays pronated as her foot is turned inward by more than 20 degrees. As our test subject begins to turn her foot in a more comfortable way, it displays normal, as it is absolutely not common to have an absolute zero pronation or supination. And as our test subject begins to turn her foot outward, our code displays supinated, since her foot is turned outward more than 20 degrees. The next test we have demonstrates dorsiflexion versus plantar flexion. As our test subject is bending her foot back with her toes up, our code displays dorsiflexion, and when she goes into a straight angle, it displays normal. As she starts to tilt her foot down, our Arduino code displays plantar flexion. In this demonstration, we're going to look into the ideal weight distribution. Quite simply, if a user has 60% of their weight on their rear foot and 40% of their weight on their forefoot, then it's considered normal. As the user starts leaning backwards, she has over 65% of her weight on her back foot. Therefore, the code displays leaning backward. Once our user starts leaning forward and she has less than 55% of her weight on her rear foot, the code will display leaning forward. For this final demonstration, we're going to look into the foot progression angle, also known as the FPA. Quite simply, if the foot is sticking out in either direction by more than 10 degrees, it will either say that the foot is turned out or turned in. Otherwise, it will display normal. So currently, as the user has her foot turned in, the code displays foot turned in, since it is turned in by more than 10 degrees.
Currently, our StandSmart product has successfully finished the proof of concept stage on a single insole. We are currently reading data from an Arduino, which is connected via USB to a computer. When we have a pair of insoles ready, we can then begin the process of measuring and testing the foot while walking, running, and other activities. After completion of calibrating and measuring the insoles for walking, we'll move on to the prototype stage, which will involve creating a PCB. The PCB we plan to design will house the microcontroller, 6-axis gyroscope, Bluetooth module, and sensor circuitry. With the addition of this board, we'll also create a cell phone app which will connect to the insoles wirelessly. This app will give the user, in an easy-to-read format, the data our StandSmart insoles have gathered, as well as any suggested improvements, if any.